Hey folks, so this first section in the algebra review is about functions, and I'm sure everybody's heard of the term before, and there's a lot of terminology about them, but I guess I wanted to first say, why do we care? What's the point of being concerned with things that are functions versus things that maybe aren't functions? Um, the the main thing about a function is consistency. It's like, well, it's sort of like having a friend that you know will tell you the truth, right? If you ask a function on Tuesday what value it sends 3 to, it's going to give you the same answer as it would on Monday, right? Every time you put a particular input in, you're going to get the exact same output out. That's consistency. That's the sense that functions are useful. So we spend a fair amount of time figuring out just how do you put that kind of consistency that in human terms I think everybody understands into a formula or into an understanding of how a function should work. So I'm going to start off just saying the definition here. This is a little bit of an old school version of it, but a function can best be thought of as being a rule. And what that rule needs to do is, like I just said, be consistent. It will assign a value to an input. And that assignment is unique. So I'll say it assigns a unique value to each element. Now I'm about to say one of those terms that I think everybody's heard before. The things that we're discussing, the inputs for a function that get sent to some value, those are members of a set called the domain. So the domain is not the same for every function. Different functions have different domains, but every function's domain is the place where its inputs can be drawn from. So that's not identical to what's given in the book, but it's quite similar. It's got the same spirit. There's a good bit to be derived from thinking about functions from multiple perspectives. Okay, so the multiple perspectives I'm going to talk about are, I think I'll list them first and then we'll go into them. But they're different ways of representing functions. Oh, that's going to be cool for me to just abbreviate funcs on the end there. So the first and most straightforward way is if you have a formula. Not a bad second thing to do is, what if you sort of could look the information, the outputs that go with a particular input up in a table? That's a pretty standard way of thinking about a function. So if you have tables, these are input-output tables. Or you may think of it as an X and a Y. Lastly, graphs. Sometimes we don't necessarily know a formula, and we don't necessarily have values that we can throw into a table, but we've got a picture for the thing. And graphs can be functions as well. Now, there's some problems with each of these. One thing is that both formulas, tables, and graphs can all not be functions. It's possible to have a table that you can just look at it and go, well, that's not a function, or a formula that no way to turn that into a function. That is, these things can all have this feature of being inconsistent, which we kind of like to not have. I think I'm going to start off by trying to expose the flaws that can happen that cause this sort of inconsistency in each of these schemes. Where's the first place to start? Well, sorry, I should have looked at my notes before I said that. Before I do that, I should give you examples of each of these things. So, yeah, let's do that first. So first thing was formulas. The way that this is where the people always write f of x, right? So f of x, which I think you've read it that way before. The name of the function is f, and x is sort of a dummy variable, really. It's a sort of an arbitrary thing that you can think of as being an input. So how about we do f of x is, let's double our x and then add 1 to it. That's a function. Now, let's just sort of analyze this. What is it about that makes us realize, yeah, that's going to be consistent? It's not going to, one time I stick a value for x in and I get an answer of 7. Good pop quiz. What value for x would give us a 7? 3, right? Yeah, 2 times 3 would give us 6 and plus. Anyway, I stick 3 in there for x and I get out 7. If I walk away and come back and go, I wonder what that thing will do if I stick 3 into it, it's also going to say 7, right? There's not going to be a problem. So how do we know this? Basically, this thing is solved for the expression f of x. If you thought of that as y, we've got it solved for y. There's an output on this side and then some formula on the other side. There are expressions that are not formulas, or that are not functions, but they don't look like this. They don't look like f of x equals and then some kind of formula. Like, for instance, this is a lovely relationship between x and y. The two of them squared and then added together gives you 1. But if you go to a GeoGebra or something and plot this, you'll see this guy's graph is a circle. It really is, and that's got a problem with not being a function. Well, how do I know that this thing isn't a function in the same way that I knew this one was? Try solving it for y. I'm going to do a little bit of algebra here, so let's see. First I'd move the x squared to the other side, and then just take the square root, no problem. Yeah, so wait, I did just solve it for y. It seemed like I said something was going to be a problem with solving it for y, and there really isn't. But it's just because I've made a mistake that you guys shouldn't make. Try not to do this. When you take a square root, you always introduce an issue of whether it's the positive or the negative square root. So really there's a plus or minus that belongs in front of this. And that's the source of the inconsistency, right? If I say, I don't know, x is 0. If x was 0, actually I can just do that by looking at that and say y squared is 1. But does that mean y is 1? No, y could also be minus 1. So we get choices. That's not cool for a function. So this guy, yes, function. This stuff, not a function. Or maybe I should make an unhappy face or something. So if you end up taking square roots in the process of solving for y, then odds are you will not have a function. There's a few other phenomena that can happen where somehow uncertainty creeps in because of the operation we're using. Okay, so that was a little discussion of how you know things are functions in terms of formulas. What if it was given as a table? I mean, I could actually present the same exact function as a table. I could say, here's x values, and here's the corresponding f of x values. Like maybe when x is 0, what would this formula give us when x was 0? Give us 1. If x was 1, that would give us 3. If x was 2, this would give us 5, etc. When would I have a table like this? This table is going to be fine, right? Because it comes from something we already know as a function. But what about a table could possibly happen where you would introduce that unreliability, that sort of thing where it's not consistent? It would be something like this. I've got 1 is being sent to 3. What if later down in the table I said, no, 1's going to go to 4? You know, that's a weird thing to do, and so I'm hoping you're looking at that and going, well, just don't do that. But if instead of thinking about the formula producing the table, I just had the table, and I looked at it and I had a pair of 1s that went to different places, I'd be, well, that's messed up. I probably almost used another word. So this can't happen. You cannot have somewhere down in the table the same x value appearing twice, and with different y's. It would be fine if this was a 3, but then it would also be stupid in this sort of a way, wouldn't it? I mean, why would you list 1 goes to 3 and then later on say, oh, by the way, 1 also goes to 3? Dude, you already did that. You know, so this is our issue. The same in paired with different outs. I guess I should actually use the full word. The same input paired with different outputs. So that, before I got it that one in, it was all good, but once that's in there, I said, whoops, not a function. Lastly, let's look at the graph situation. Everybody heard of the vertical line test? That's really what we're talking about here. So when you have a graph that is a function, it passes the vertical line test, and if it's not a function, it fails it. So why? Well, here's a function that passes the vertical line test. I have no idea what that formula for that would be, but some kind of crazy looking wiggly curve. And here's a graph that fails the vertical line test. Now, at some level, these are both just weird-looking curvy things, right? But this one's kind of a good weird-looking curvy thing, and that one's a bad one. Why? Think about what happens at a particular input. I say, suppose here's a spot on the x-axis, we'll call it x. And I go, well, the y that goes with that is just look above me and find the graph. That y is what comes out. I would probably call it f of x, actually. And that height is the output that goes with this input position. Well, what about over there? Depends where you do it. If you're over here, if x was there, it's fine. You come up to here, you got your unique output that goes with that input. But what if you're here? If x was, well, okay, kind of erase that one. If x was there, which one of these different places would I choose as the output that goes with that input? Can't have choices like that. Can't have that sort of ability to be inconsistent. X has got to go to 1 and only 1 in output value. So that's a vertical line that's hitting the graph multiple times. And that's a place where you fail the vertical line test. Almost everybody just understands that abbreviation, so I don't think it'll be. This one, on the other hand, you can draw vertical lines wherever you want. It's all good. They hit it once and only once. This guy, there's a bunch of spots where you hit it multiple times. Right there. It's weird to say this. Failure of the VLT, you fail it if you fail it even at once, right? Just a single vertical line that hits the graph more than once is enough. So for instance, let me show you a graph that many people would go, that's fine. Suppose I had a graph that looked like that, a wiggly, curvy thing, but you see how it's passing the vertical line test? But there's also one point that's not on the line, not on the curve. Well, if you make a vertical line right there so that it goes through that point and also hits the graph, That's a problem. You've got a place where it fails VLT. Okay, so let's talk about those sets. I mentioned one of them, domain. Interesting etymology of that word. The domain has the same Latin root as the English word domicile, which is the place where you live. Domestic, things that have to do with where you live. Domain is kind of where the function lives. So the domain, and by the way, the way to write that, let's just say the domain is written using a notation that actually looks a little bit like a function. You write dom of f. So if you've got a function hanging around, write dom of f, and you'll get the set that is its domain. Well, maybe I can make a sentence out of this. The domain of a function is the set of all input values that kind of work in that function. Basically, well, you've probably seen a bunch of examples of this in your algebra career so far. There's some things that just break a function or break a formula. It can't handle it. Like, you know how you can't take the square root of a negative number? If you can do whatever the operation is, we say the function is defined at that point. So the way I'm going to write this or end this sentence is to say, we're talking about the set of all x's such that f of x is defined. Which is a slightly unusual use of the word defined. I don't mean like defining a word. I mean saying that at that x value, we can actually come up with a y value. We can come up with an output value. So, well, the way I defined a function, that was sort of automatic. It was the things that, you know, it was the x values that the function assigned somewhere. Often, though, a function is handed to you with a formula or a table or something, and you have to guess what the domain is. An example of this might be the square root function. I just mentioned that. F of x equals square root of x. What's the domain of that? You know, you can you take a square root of 0? Wait a minute, is that all right? Yeah, you can. 0's square root would be 0. And positive numbers are fine, and anything above 0 is going to be all right. So what isn't okay? Negative numbers. There's a couple of ways to specify the domain. One would be just write an inequality like this. X has got to be greater or equal to 0. Another option, if you're familiar with it, is the interval notation for that same region. Everything from 0 off to infinity, headed to the right. 0 to plus infinity. And the 0, you remember, I think you've seen this, but if not, a square brace means that includes that value. It's a little bit like the equals part in the x is greater than or equals. You can't actually get to infinity, so traditionally there's a parenthesis there. But generally speaking, you use the round parenthesis for values that you kind of go up to them, but you don't ever quite get there. All right, so that's one of these sets of interest. The other is, well, I mean, this one has to do with the inputs. The other thing to consider is the outputs. That is called the range. And I would say, maybe I should capitalize it the way I did domain. The range of a function, and I believe they misstate it slightly in the book. It's the outputs that literally do occur. That is, there is some input that gets sent to that output. there's another idea about sort of the range, and it's that maybe you should sort of look at the potential outputs, the places that the function was kind of aiming at, right? But that's not what the range literally means. It's not where you know, I mean, you might say all real numbers all the time if you just meant where you think your outputs are going to lie. But we want the outputs that literally do occur. So, for instance, let's do this function, the square root of x. The outputs of that are, well, when x is 0, you get 0. Can you get any number bigger than 0? Yes, you can. And by definition of this function, it never reports the negative square root. It always just gives you the positive one. So this guy's got a range that's the numbers from 0 going up. Now that's really in the y direction, but we still kind of write the thing horizontally. So wait, these two things were our domain, written like that. I'm just going to squeeze it onto the board here. The range is usually abbreviated like RNG. And in fact, if you write it in interval notation, it looks the same. Right? It would be 0 and any number bigger than 0, all the way up towards infinity. If you write it as an inequality, it would probably be y is greater than or equal to 0 instead of x is greater than or equal to 0. But still, it's the same inequality, just changing the letter. All right, so that's our domain and range sets. The last thing in that little section is there's sort of they call it toolkit, a compendium of reasonable, simple functions that we kind of need to know how they look. And I should kind of give you a heads up on where this is heading. You've got this little list of 7 or 8 functions, and then we're going to have ways to change them. We're going to have ways to move them around and shift and stretch and do all kinds of operations to them. And so the idea is to have this small number of sort of basic tools, and then ways to modify them, and ending up with a lot of freedom where you can create functions, curves that look like a particular realistic situation. Yeah, so that's the plan. We're going to have our basic toolkit of simple functions, and then we're going to show how to modify those to make a whole bunch of different functions. So what are the basic guys? Well, the first one is almost too stupid. It's a function that always responds with the same answer. Its f of x is just equal to a constant, or k is traditionally used, or sometimes c, but k and c are used for constants. So what I've written there is the constant function. I sometimes do this activity with classes. It really has to be in person to do this, but I'll think of a function and then ask you guys to quiz me on it. And basically, I ask you to come up with an input, and then I'll tell you what's the output that goes with it. So the constant function makes me sound really stupid because, somebody says, well, what does it do with 1? And I say, you get 7. And then I say, well, what does it do to 2? Also 7. What does it do to 17? Oh, 7. It's a function that just basically ignores its input and always responds with the value, the constant. Okay, so that's not a very exciting one. There's another one that's also in a way not very exciting, and it's only slightly less stupid. This is called the identity function, because what does it do? It sends x to itself. If you played it in the guess what function I am game, I sound like a parrot. A student asks me, what's the value at 3? And I say 3. Why are you just repeating me? So, Yeah, it seems uninteresting, but when you put these two together, you get lines, which that's an important category of function. I should say more about it. You put these two together with the manipulations that we're going to talk about in a sec, and then you can get all kinds of lines. How about this one? You guys know the absolute value function, where you have vertical bars around the input? That's just if the number's negative, it turns it positive, and if the number's positive, it leaves it alone. It's the identity function on positive numbers, and it's like the negative. Oh, well, it's like drop the minus sign off of any negative inputs. Then there's a couple of things that are given that sort of fall under the realm of powers of x. Generally, they're known as power functions. Oh, I was going to name these as x. This one is the absolute value function. I'm going to give, I kind of want to give a bunch of examples at the same time, so let's just say x to the n power. N can be any number, including numbers like, -3 or +7. So it's okay to have negative exponents. That's a weird thing we'll talk about in a sec. Well, so that's not just one example. Each of these was a single example. That's a whole bunch of examples, and those are generally known as power functions. The ones that are listed in the book are n is 2 or 3. 1 wouldn't make sense because that's the same as this one. 0 doesn't make sense because that's one of these with k equal 1. But -1, you can have x to the -1 power, that's just the same as 1 over x. -2 is 1 over x squared. Anyway, we'll see that. But what the future has in store for us is to take these basic toolkit functions and then do more stuff to them to get kind of a nice variety of different things. All right, so the next little piece we're going to deal with is hardening up what I meant about functions, ways of transforming a function. Take one of our existing things from the library there and make it look a little different. But before we go into the transformations, there's one other way of sort of putting two functions together. That's kind of a big deal. And so, and to be quite honest, the other things, the things that we're going to look at that transform a function into something that's similarly shaped, can be thought of as being examples of this. The thing I'm referring to is known as composition. So a common way to sort of visualize functions is by what engineers call black box diagrams. You have an input and an output diagram. And the point of this, if you're doing like electrical engineering, for instance, you just don't really care what's the guts, what's happening inside of there. There might be some complicated circuitry, or it might be just a real simple thing. All you care is what's the effect, So X goes in, something happens to it, and what comes out? F of X. This is a good way of sort of visualizing composition, because all composition means is take two of these things and wire them together. So here's a composition. X goes into F, and something comes out, but right away, we don't even check what that value is. We feed it into another black box, and something else comes out. Now let's figure out what happens here if you have that kind of a circuit diagram. X feeds into here, and actually we do know what's on that line. What's on here is just what it was there. It's f of x. But now we're in a messed up situation for G because its input isn't x. The input has already been changed to f of x. So what comes out of here is G of f of x. Now, there's a funny thing going on here that you have to get used to. Notice what order these operations happen. F happens first, right? X goes into F, it gets modified, and then G happens second. But if you read this left to right, as we're used to reading things, it seems like G happens first and then F. So just notice that you need to look at that and think about it as reading right to left. Just a little fine business. But if you kind of stare at this for a second, you realize, okay, F is consuming the input first and modifying it, and then G is getting that change thing out. So it's really that way of parenthesizing things means F happens first and then G happens, not vice versa. So a common example of this kind of diagram happens when you put machines in the place of the boxes. And I often give this as a thought exercise for students. Can you think of some actual machines where you can compose them like this, where one thing gets an input, modifies that input, the output, the modified thing, goes into the other machine, and finally a third thing comes out. A great example is this could be a washing machine, and that could be a dryer. So what is X? Dirty clothes. They come out of the washer, and they're wet clothes. Clean now, but wet. Stick them in the dryer, and what comes out of that is clean and dry. So you go from dirty to clean and dry if you think of this as one entity. The composition is exactly that, the one entity. So when you think of it that way, the two machines together being one bigger machine, that guy is GOF. The circle is supposed to be a little bit smaller than I just drew it. GOF. No, I probably made it too small. But that composition of G and F in this order, and again, you see the reversal. F is on the right, G is on the left. But that means do F first and then do G. FOG of X, that's a function that takes an input X and ends up giving us the output G of F of X. So I would encourage you to think about other pairs of household appliances you might be able to put together. Some of them work and some of them don't. Right? Like, for instance, if this was a washer and a dryer, can I put them together in the other order? Stick my dirty clothes in the drying machine and bake them for a little while, and then stick them in the washer, and what's going to come out, I guess it'll be clean, but it will still be wet. I haven't done things right that way. So the order matters. This is one of those times when you can't just flip orders around. Functional composition is not a commutative thing. So we need to sort of look at this composition of two functions using those three different perspectives that I talked about before: formulas, tables, and graphs, and see how it might play out. So let's look at composition using formulas. Suppose f of x is, how about 3x plus 2? Just making up a random one. And g of x is, how about x squared minus 1? So if I want to get FOG, what would that be? FOG means this is the version where you do G first, and then you feed that into F. So I usually write this starting on the wrong end. I'll look at F and go, all right, write it, but instead of using X, leave a blank. So the formula for F is 3 times its input, let's leave a blank for that, plus 2. Okay? Now, when we have this composition FOG, G happens before you stick it into F. So the blank I've written there needs to be filled in with the formula for G, which would be x squared minus 1. Okay, now the underline looks stupid, so I'm just going to take the underline away. But, you know, that was, conceptually, it was there for us to think about. Filling in the blank with the formula for the first function, the g. You could do some algebra with this, but that's not very much. I guess you can distribute the 3, and you get 3x squared minus 3 plus 2. Oh, and then you can combine those two. It ends up being 3x squared minus 1. Let's, while we're at it, looking at this formula, let's take a look at what the other composition would be. What if we did GOF? Now, how do I do this? Now I want to write G's formula, but replacing the x with a blank. G's formula is square its input, and then subtract 1. And its input is going to be whatever f did to x. F tripled it and added 3. So 3x plus 2. I'll take the blank away. So that's interesting, right? GOF, man, those are going to end up being pretty different. You can, to simplify this, or to figure out what that really is equal to, you use the infamous FOIL rule, because you have to multiply 3x plus 2 times itself to get it square. And so the first term in it is going to be 3x times 3x, first times first, which is 9x squared. It's already a lot bigger than this one. I guess I might as well. I'll go ahead and do this, even though we haven't really talked about how to manipulate quadratics like this. Get 9x squared plus 12x plus 4 minus 1. The only thing that can be simplified is the 4 minus 1 gives us a 3. So that and that, definitely not the same. GOF and FOG, generally speaking, are not going to be the same. All right, so that's the idea of composition for formulas. Let's take a look at it if we have tables for our functions. Suppose, about to use red. Suppose here's a table for F. I'm going to go 0, 1, 2, 3, and frankly, I'm just going to make up numbers to go in here. Minus 1, 2, 4, 5. And here's a table for G, X, X. Oh, sorry, G of X. I'm going to be a little more expansive on G, because I need to be. I accidentally spread these out a kind of a bit. But, -2, -1, 0, 1, 2, 3. Okay. And again, I'm just going to make up numbers. As long as I don't have repeats in the x column, it's cool. You can have any values you want to on the left. So 5, 6, 7, 8, 9, 10. All right, so what if I wanted GOF of 2? I would say, well, sorry. Let me do one that works first, and then we'll show you one that doesn't work. How about if I did GOF of 1? So what we would do is look up what this function f does to the input 1. This was the right row. It gives us a 2. Right? And then we'd stick 2 into this other function. I mean, we have to go down its table until we find the 2, and then we look across from it and we get 9. How about the one that I started to do, GOF of 2? GOF of 2, f sends 2 to 4, right? And then what does G do with 4? Well, crap, I didn't say. So I'm off the edge of the table. If I had taken it one more step, maybe it would have something. But right now, all I can tell you is we don't have a value defined. There isn't an output. It would be G of 4 if I knew what G of 4 is, but that number is undefined. And so all you have to do, unfortunately, you have to write this out when it happens. If there just isn't a value for the output, you just write the word undefined. So that was formulas, tables, oh, graphs. Graphically doing composition is a pain in the neck. I won't lie to you. It's sort of the least intuitive thing here. But let's graph the two functions I'm interested in separately. So this will be a graph of f, maybe like that. And here's a graph of g, like that. Now, what I have to do to figure out GOF is best done on top of this graph, on top of the graph where f is. So what do I do? I take a particular input. You have to do this by plotting a whole bunch of input values, but suppose that's the input I'm interested in. Well, I'll get how much, what is this y coordinate, or this length I'm just shading in there, is what f does to that input. If this value was 1, it looks like that y value is maybe 1.5. Great. Then I have to come over to this side and turn that bar sideways, right? And put that same length right on here on the x-axis, because I want that output to be viewed as an input on this guy. And then I get an output. And then, finally, I take that y-coordinate and come back over here. That's a spot that's on GOF. Wow. So this sort of graphical work to compose things with functions, it's not easy, and it's rarely necessary. So almost always what we're going to be doing is either the tables or the functions. But you should see that it's conceivable to do this. You might use a ruler or something and go around and plot a whole bunch of different points. I think maybe I'd plot a point here. I get that value. I come over here and say, well, that comes to this height. And so, oh, it looks like it lands on almost the exact same spot. It's weird. All right, so that's composition viewed in sort of all three manners. Let's finally look at some real simple functions that we can compose with other guys once ahead of time and once afterwards. That is, you'll sort of think about an f, and you'll have something you can put in front of it and something you can put behind it. That's easy. The very first kind of transformation we're going to get is from using a simple function well, I'm going to call it t of x, okay? Transformations, not things. What I'm talking about is actually shifts first. So if you have let's call it s of x, not t of x. S of x looks like this: x plus some number, some constant k. Now that's actually combining our identity function and the constant function, adding them together. All right, so if I given a particular function f of x, if I then do this to it, what is the effect of that? Well, you take the formula for the outer function, s of x, and where it had an x, leave a blank, and then you plug f into it. So this is just going to look like x blank plus k, but the thing that's going to go in there is f of x. All right, so maybe that was a silly way to say it. What does this do overall? It just takes whatever values f had at x and adds something to them, adds that constant to them. So what this shifting does, this s of x thing does, if we compose it on the outside like that, it shifts us vertically. This is just a vertical shift by k units. And if k was negative, that would mean a downward shift, right? You could go up with positive k's, downward with negative k's. let's look at what we get if we do this composition the other way, f of s of x. Well, that means f is in the spot where we write f and it's blank, a blank where the x's are. And then the shift function is x plus k. So what does that mean? It's a little hard to conceive of, but what's happening here is you're adding k to the x value before you feed it into the f. So what gets plotted at a particular x coordinate is not the function value that goes with that x coordinate. It's the one that goes somewhere down the road, k units farther down the road. The best way to probably view this is to do it on GeoGebra and see that you can actually make a thing where that k is a slider, and you change the slider and see what it does to the graph. But it horizontally shifts by k units, except in the wrong direction. We get a horizontal shift, but it's going to go negative k units. So the way people often do this is replace the shift function with x minus the constant. But I'm just going to write it as negative k. So folks sometimes refer to these as inside and outside changes. If you have the shift function on the inside, you get a horizontal shift. And inside changes, generally speaking, work backwards from the way you might expect. Outside changes are nice. If you add 3 after the function's formula has been computed, you're just going to move everything up by 3. So you'll move in the same direction you expected. Inside changes are tricky. They kind of work backwards of what you expect. So that's shifting in a nutshell. I mean, we can do that with real examples. Let's do one. Let's do a simple one. Suppose f of x equals x squared, which I think we all know the graph of that looks like a kind of a U. It's parabola shape, it's known as. What happens if we make an outside change by adding a 1 on the end? So how about we make it g of x now is f of x plus 1, so it would be x squared plus 1, an outside change. What does it look like? Just the same thing, but pushed up in the air a little bit more. The same. Well, my drawing could be a little cleaner, but still, it's as if you just grabbed this thing and pushed her up until it moved 1 unit. But if you did that, adding 1 on the inside, we'll call a new name h of x. It would be x plus 1 squared. That actually, you would think, okay, it's a plus 1, that means it's going to move to the right, but it doesn't, it moves to the left. How to think about that? What you plot at 0 is what our original f would have plotted at 1. Right? The input has been changed by adding 1 to it. So what we plot right here is this value. And then what we plot at minus 1, that's what we get. If minus 1 was in there, you'd have 0 after you added 1. And f applied to 0 would give us 0. So that's one. Well, okay. The end analysis is that the parabola just got pushed to the left. Vertical shifts, all good. Horizontal shifts, they work backwards. Just remember that, it'll be cool. There's two other, well, in the book they present these as 2 separate things. I kind of view them as one as an example of a special case of the other. So instead of adding something, either on the inside or the outside, what if we multiply by something on the inside or the outside? So what I just looked at was s of x equals x plus k, but how about if I looked at s of x equals x times k? Okay, if we do that on the outside, it just looks like you start with f of x and you transform it into some number times f of x. You just multiply it by k. I multiplied by k on the right, I could multiply by k on the left. That is something where you can switch order because it's just multiplying. Well, I think that's pretty clear what that does. Like if k was 2, whatever the graph of f of x is, the graph of this thing, this transformed version of it, is twice as tall because you multiply by 2. An interesting case happens when k is a negative number, though, which is well, in particular, what if k was -1? Then you're going to take the graph of f of x and flip it upside down. Where the outputs were positive, they'll become negative. So, for instance, let's do an example of this kind of a change. Suppose f of x was the absolute value graph. And I'm going to multiply on the outside by -1. So we'll call it g of x, but it's going to be -1 times the absolute value graph. Anyway, yeah, what happens to the graphs here? Let me quickly sketch it for you. The absolute value graph looks like AV. Looks like that. If you multiply on the outside by -1, it's going to turn that V upside down. So this is actually a mirror image kind of effect. So, you know, the upright V turned into an upside down V. And so multiplying by -1 on the outside, that is reflection in the x-axis. Interestingly, if you put that minus sign on the inside, let's think about what that would do. I better call it something else. How about if we said h of x is the absolute value of -x? Well, that's going to be reflection in the y-axis. Really pointing at the wrong spot, I should say there. That's reflection in the y-axis. And in this particular graph, if you think about what its mirror image in the y-axis is, it's the same thing. You know, this line ends up over there, and this line ends up over there, but they land back overall, and you've got the same set of points. Okay, so that's a weird graph. It does nothing if you reflect it across the y-axis, but it does something fairly radical if you reflect it across the x-axis. We often look at these kinds of reflections and ask, you know, does that change the graph or not? And if it does, or if it doesn't, it tells you what sort of symmetries are involved in the formula. So what we just started with is f of x being transformed by multiplying by k, and that did vertical stuff. Similarly, if you multiply by k on the inside, you'll get horizontal stuff. And like I said a couple of times, those inside changes, they kind of go backwards. So let me synopsize this, and then we'll be done for today. If you, oh, that's not a good marker. If you start with an f of x and you transform it by multiplying on the outside by some constant, that scales vertically by k. big number, it stretches it a lot. If k is a small number, it can actually compress it, it can make it little. If k is negative, it can turn it even upside down. But you can even have a negative large number, which you could view as stretch it out and then turn it upside down. So you've got a stretched out upside down thing. If you start with the same function, but you make the change on the inside, you now will scale things horizontally. But the factor is actually 1 over k. So if you, for instance, you multiply by 2 on the inside, it's like it got squished horizontally and it gets half as wide as it used to be. Right, so the general thing here is, the last thing to say is you can take all these operations we've talked about, adding or multiplying on the inside or on the outside, and mix and match them to make all kinds of weird things happen. Like, an example would probably be in order of that, for that. I've got a better marker here. Here's the graph of y equals x squared. What if for some phenomenon I was trying to model, maybe to solve a business problem, I needed to see something that looked like this? Well, that does not look like my y equals x squared, at least not at first, but you can kind of put a couple of operations together until it does look that way. For instance, what if we scaled it by a factor of a negative number to turn it upside down, and maybe a half? Okay. So you could turn that guy upside down and make it half as tall. And now it has kind of the right form, but it's not in the right place. Well, that's our shifting, right? Now I just need to move it over here and move it up to there. So I might start with f of x equals x squared, do some scaling vertically. In this case, I only need to do vertical scaling, and then some shifting. But this guy probably is some, I'm just guesstimating where the looks like we went 4 sideways and 2 vertically. So how about it's g of x would be negative a half times, we'll have to work out what do we square. But here, the adding part I can get. To move it vertically up, I needed to add the 2. How do I move it sideways? Again, this is a moment where you got to remember the shifts go backwards. So if I want to move 4 to the right, I actually subtract 4 on the inside. All right, so that's a full day. We'll stop there.